Good day. There we are. Okay, we're going to find the center of mass of a doorstop, a triangular solid of mass m, length L, and height h. And we've jotted down the list of steps that we'd like to take in order to find the center of mass using the fancy integral version of the center of mass formula. So let's do this. We start off by step one, defining a coordinate system. And I will do that by placing, in this case, the narrow end of the doorstop at the origin of a coordinate system. I've got my y-axis pointing up and my x-axis pointing to the right. It is possible that you can set up a coordinate system and make this problem easy or hard to do, but you definitely have to, so there might be one better way and one worse way to do it, but you definitely have to start off with a coordinate system in place. You might change your mind later on. This one's going to work for this problem. Okay, step two is to take this doorstop, this triangular solid, and divide it into a bunch of mass elements dm whose center of mass you know the location of. So what I mean by that is there's a lot of ways I can divide this into infinitesimally small masses that whose center mass I don't know the location of. If I were to, there's the bell, if I were to divide this up into a bunch of slices like this, we're not going to do this. If I were to cut it up along some weird angle like that, one of these pieces, here's one of the very narrow pieces here, an infinitesimally small amount of mass, that's a nice little tiny, well actually just between here and there is where I have the mass of the doorstop. That's a very nice thin piece of mass, but I don't know where the center mass of that piece is. It's in the middle somewhere. I guess kind of like in here is where its center mass is, but I have no way of specifying where that is on the x-axis or anything like that. It's, you know, I've got to figure out some angle or do some weird geometry to find out where that is. That's not a helpful way to do this problem. So I'm going to get rid of that, I hope. Go away, blue lines. Okay. In this case, the logical way to do this is to cut this into tiny pieces, each of which has all of its mass exactly above one location on the x-axis. So there's an infinitely thin slice of doorstop, and all of its mass is at one particular value of x on the x-axis. Here's another one up here. And this little tiny piece of doorstop has all of its mass above a different value on the x-axis. The first one might be at the 20 centimeter mark, and the second one might be at the 40 centimeter mark or something, depending on how big this thing is. So, okay. So this is how I'm going to divide up this doorstop into tiny pieces of mass. So I've done step two. There, in fact, are an infinitely large number of these pieces. I've drawn two of them, and then I got tired of drawing, so I quit. All right. But this represents exactly how I am. I'm cutting this thing up into little tiny bits of mass. Okay, step three, write the center mass definition. 1 over mass, the whole thing. And then I'm going to add up, integrate all these products of the mass of each piece times its position on the x-axis. And that's what that symbol means. Integrate means add up all the x dm products. All right. So now what I'd like to do is actually do this mathematical integration, but I can't do that until I have reduced this down to one variable. This is what I mean. I have, in this equation, I've got three terms. I've got big M, I've got x, and I have dm. Big M is the mass of the whole thing. That's a constant. It doesn't change. dm is next. dm stands for the mass of each of these little pieces. Well, they're all different amounts of mass. That's a variable. And x stands for the position of each of these little pieces. That also varies. One's at 40 centimeters, one's at 80 centimeters, and so on. So I've got two different variables, and I have to reduce this to one variable before I can mathematically do the integration. So here's how I do it. I typically try to think about the mass of each piece and whether I can express the mass of each piece in terms of x as a variable, constants, and dx. And if I can do that and then substitute in to get the dm out of there and put in some x's, some variables, I'm sorry, some constants and dx, then I'll have a function of one variable that I can integrate. All right. The way I typically do this is I examine each of these pieces, and I also think about one of our different versions of density that we have been using to describe how the mass is distributed in these things. In this case, I have mass distributed over an area. In other words, this thing is essentially a two-dimensional figure. And so I'm going to consider the area mass density, sigma, mass per unit area, for this shape. Let's see how this works out. The first thing I'm going to do is find the area mass density. And by the way, as a trick, not as a trick, as a rule, what we usually do is if something is one-dimensional, like a stick, we consider its linear mass density. If it's two-dimensional, like this doorstop, the mass is spread out over an area, we think about area mass density, sigma. And if it's three-dimensional, like a parsnip, say, or a cone in that shape, then we think about how its mass is spread out over 3 dimensions, and we use volume mass density. Okay, so I'm going to use area mass density. Sigma is mass over area. And I'm just over on the left here, I'm going to more specifically say what that is for this particular shape. In other words, I know this thing has mass m. What is its area? Well, this doorstop, this triangular solid, has an area found using the triangle area formula, which is 1/2 base times height. So I'm subbing in for A. The base of this thing is L, and the height is big H. So this turns into 2m over LH. That's the area mass density, the number of kilograms per square meter of mass on this doorstop. All right. Can I use that to express the mass of each individual piece in terms of constants x and dx? And it turns out that I can. Consider one of these pieces. I'm going to shade this in red, if you can see that, on the original shape there. How much mass does that have? Well, it has an amount of mass which is equal to density times area. If density is mass over area, mass is density times area. But I'm using the sigma for density, but I'm putting in dA because the area of this little tiny piece is infinitely small. Okay. Well, what is the area of that piece? I'm going to scroll back up again. Well, the area of that piece is found by considering what shape it is. And the shape of this piece is a rectangle. I know that the top isn't actually completely flat. I just misspelled rectangle. Okay. I know the top isn't totally flat because this thing is so infinitely thin, the fact that the top of it is actually at a slight angle doesn't in any significant way change its area. So I can use a rectangle formula, which is length times width. This is getting cluttered up here, so I'm going to write this down here. dA is length times width of that rectangle. Okay, what's the length? What's the width? I never remember which one's length, which one's width. I'm going to call the length the right to left. From right to, that's supposed to be a little double arrow thing. How far is this thing from right to left? Infinitely thin. That length, if you will, is dx. It's a tiny, tiny step along the x-axis. That's the length of the rectangle. How wide or high is the rectangle? Well, that is not infinitely small. That's several centimeters or something. For now, I might call it little h. So I can write the area of this thing as h times dx, the area of the rectangle. Which means I can go back to my dm mass here and say sigma times h dx. Okay, that's very nice. Remember what I'm trying to do here? I'm trying to reduce everything to one variable. I'm trying to substitute in for dm right here and get rid of the dm and put in a bunch of constants, x and dx. Let's see. Let's check what we have here. Sigma, that's a constant. H, is h a constant? The answer to that is no, because each of these different pieces of mass not only have different addresses, different x's, they also have different h's. They have different heights. One of these is taller than the other one. They all have different heights. So that's a variable. I got to get rid of it. I want to reduce everything to one variable, x, dx, and constants. Okay, a new challenge. How do I express h, this height, in terms of constants in x? Well, there's a couple ways I can look at this. I'm going to go back actually just to my the rectangle on the right, the mass element on the right here. There's a couple of ways I can look at this. One is through similar triangles. Consider this smaller triangle that I'm outlining in green, which has as its base from the origin to the mass element. The vertical height is h, and then the third leg is the hypotenuse, only as far as that mass element. Okay, this triangle has height, h, and the length down here on the bottom is x. That's the position of this mass element. So it has sides of h and x. There's another triangle here, which I'm going to outline in huge yellow, and that is the whole doorstop. That has analogous sides L and big H. Well, those two triangles are similar, and so because they have the same angles, and so I can set up proportions. I can say that the vertical side, H over the horizontal side, X, that's the little triangle, is equal to big H over L, that's the big triangle. So the sides are in proportion to each other. That allows me now to say that little h is equal to big H over L times X. I'm just rearranging. This makes me very, very happy because I can now plug in for h, dm equals sigma times h, but I'm going to plug in big H over L times X times dx. Okay, what do I have? I have constant sigma, constant h over L, variable x, variable dx. Is exactly what I've been aiming for. I now have reduced everything to one variable because if I now plug in for dm, I'm going to rewrite this original definition down here at the bottom so I have a place to work. If I rewrite the original definition, xcm is 1 over mass integral x dm. Okay, I'm going to plug this stuff in for dm. Let's see what I get. 1 over mass integral x times dm, which is sigma h over L x dx. Okay, I'm giddily happy because I now have only one variable in there. It appears twice. I have to be careful. I've got an x, and dx. Everything else there is a constant, so I can pull that out. X cm equals, let's see, sigma h on top, m L on the bottom, integral x times x is x squared dx. Now I can solve this thing. Now I can actually do this integration. And now I have to consider over what domain am I actually integrating this function? Over what values of x is this a legitimate function? Going back and looking at my picture, the first value of x is 0, and the last value of x that I'm going to find these slices is big L. So I'm integrating from 0 to L. Okie dokie, so I'm integrating from 0 to L. Let's do this bad thing. I'm going to scroll this up a little bit more. Okay, sigma over h. What do I have to plug in for sigma? I've got that up here somewhere. 2m over L times h. I'm going to plug that in for sigma. Sigma, instead I'm going to put 2m over L times h. Times h over m L. That's all the constants in front. Times integral of x squared dx. Okay, this is of the familiar form now of kx to the n, and the integral of kx to the n times dx is equal to k over n plus 1 x to the n plus 1. We've actually taken all the constant out already, so we don't have to worry about that. It's just 1 over n plus 1 x to the n plus 1. In this case, n is 2. So that means I'm going to get 1 over 2 plus 1, or 1/3, x to the 2 plus 1, or 3. And then I'm going to plug in the limits, 0 and L, and evaluate at those two different positions and subtract. We're almost done. Okay, I can do some canceling. Let's see, I've got h and h. I've got m and m. These L's don't cancel because they're both in the denominator. So I have xcm equals 2 over L squared. That's what I have left in front. And then I have x cubed over 3, and I'm going to plug in L for x. So I get L cubed over 3 minus the lower limit plugged in, and that's going to be 0 cubed over 3. That one's tough to evaluate. That goes bye-bye. Arrow 0. And I am left with, I think that was pretty straightforward, I have 2 over 3. L cubed over L squared is L. Done and happy. 2/3 of the way from the skinny end to the fat end of the doorstop. The end.